In fitting a linear model, we have seen that the bottom line is we want to regress our dependent variable on either one independent variable, which is the simple linear regression model, or we wish to regress the dependent variable on a number of predictor variables, which is the case of multiple linear regression. But in case of multiple linear regression, we usually have a number of predictor variables. Sometimes all of these predictor variables are important for the study. However, sometimes some of these regressor variables are not significant and they can be removed from the model. Now, in this module, I will discuss three different methods of selecting variables that we can add to the multiple regression equation. We will see how we can use R to keep the significant variables in our regression model and how to discard the redundant ones. The principle of Occam's razor states that among several plausible explanations for a phenomena, the simplest is the best. The same is true when we consider variable selection in regression. We wish to identify the best subset among the many variables that we use to regress our dependent variable y. The idea in variable selection, keeping in mind what I just mentioned in item 1, is to keep only those explanatory variables in the model that actually significantly affect the response variable. We wish to find the simplest model that fits the data best, and I have put simplest in quotation marks because sometimes the simplest model might be the one which has a large number of variables, but if they are all very significant, then we have to include all of them in our regression model. Now, if we have unnecessary predictors, when they are added to the model, they add noise to the estimation of the parameters that we are actually interested in. If you remember the way we had written the multiple regression model, it looks like y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta p xp plus epsilon, where epsilon is our error term and x1, x2, xp are the p regressor variables or p predictor variables, and in addition to these we have their corresponding regression parameters beta 1, beta 2, beta p. Now, if we have unnecessary predictors added in our model, then that increases the number of parameters that we have to unnecessarily estimate. Now, sometimes adding too many explanatory variables can be a cause of collinearity between the explanatory variables. This is one of the other consequences of adding more variables in a data set. Suppose we have two variables as predictors which are very closely related to each other. Suppose our dependent variable is expenditure and our independent variables are the amount of money spent on luxury goods and the income of the person. Then these two variables, the independent variables, are quite correlated to one another. So, adding both of them in the model might lead to faulty inference on the parameters. So, including any one of them should be significant enough, and that is what we wish to test here, and then keep the variables that are significant and remove the ones that are not. So, using a simpler model with less number of variables is also cost efficient. We can save both money and time by not measuring the variables which are redundant. Now, let us first talk about hierarchical models. I had just explained the multiple regression model, which is of the form yi equals beta naught plus beta 1 x1 I, beta 2 x2 I, beta p xp I plus epsilon. But we sometimes come across models that have a natural hierarchy. For example, a polynomial model with two variables x and x square, where x square is a higher order term than x. Now, consider the model y equals beta naught plus beta 1 x plus beta 2 x square plus epsilon. Suppose in this model x square turns out to be significant where x does not. Then we remove x and write the model with only x square. Now, if the scale is changed so that x now becomes x plus a, then the above model would look like y equals beta naught plus beta 2 times a square plus 2 beta 2 times ax plus beta 2 times x square plus epsilon. As you can see, this scale transformation now brings back the term x into the model. Since we see here that the hierarchical model, removal of lower order term can be troublesome because then the scale change makes a significant change in the model. So, removal of a lower order term cannot be justified in most of the hierarchical models. In this module, we will look at 3 procedures for selecting the significant explanatory variables and removing the ones which are insignificant. The 3 different variable selection techniques will be discussed and also illustrated using R. The first variable selection method that we will discuss here is called the backward elimination method. This is the simplest of all the selection procedures and can be implemented even without the help of softwares. We start with all the predictor variables included in the model. Thus, if we have 10 predictor variables, we start with a model that contains all of these 10 variables in the model and we fit a regression line. After fitting the full model, we inspect the p-values corresponding to each of the predictors and we eliminate the predictors that have p-values greater than the level of significance alpha fixed by us. The above 2 steps are then repeated until we are left with only those variables that are statistically significant. So, in short, in backward elimination, we start with the whole model. Suppose 10 predictor variables are included in the model, and after inspecting the p-values, we see that out of these 10, 2 of them have p-values which are greater than alpha. So, we eliminate those predictors and keep the remaining 8 and perform the regression analysis once again, and we again inspect the p-values and eliminate the predictors that have p-values greater than alpha and retain the rest, and we keep on repeating these 2 steps, and finally we arrive at the model which only contains variables that are statistically significant. We can also obtain a subset of the predictor variables using backward elimination method by using R. In the next few slides, I will illustrate how to use R to select significant variables. In this example, we have used the state dataset, which is a built-in dataset in R. The variables in the dataset are population, income, illiteracy, life expectancy, rate of murder, number of high school graduates, frost and area. The response variable here is life expectancy and the other variables are all treated as predictors. So, here is the code to attach the data set to the R console. We write data within parentheses state, which will attach the data set and we convert it to data frame. And using the function step on the LM object of life expectancy, regressed on all the other variables, and we also mentioned the direction as backward, we can perform the backward elimination method in R. Now, let us look at the output that we obtain by using the step function. So, we start with the AIC of the whole model, the model which contains all the response variables, all the predictor variables in the model. The AIC is negative 22.18 for a model of life expectancy regressed on population, income, illiteracy, murder, HS graduate, frost and area. And underneath that, in the tabular form, we have all of these variables, the predictor variables with the negative sign attached to them, which means that we have fitted the model again, and each time we had removed that particular predictor variable from the model and computed the AICs. So, the first is we removed area and we fitted the model again and obtained the AIC, which was negative 24.182. Next, We had removed negative income and obtained the AIC as negative 24.175 and so on and so forth for each of the predictor variables. And after we had done that, we have ordered the AICs. We know for AICs, the smaller the AIC, the better. So, the smaller AIC, smallest AIC, negative 24.182, which is corresponding to area. We removed area and we now in the second step fit the model again. So, in the second step, as you can see, the AIC of the model is negative 24.18, which was corresponding to the model with all the predictor variables included except for area. So, we now in the second step again go through the same steps of removing one of the predictors at a time and fitting the model again and obtaining the AICs. We have again ordered the AICs. So, we know that the AICs, the greater, the better the model. So, the one with the lowest AIC, which is negative 26.174, which is corresponding to removal of illiteracy, is the model that has the lowest AIC. So, we remove the AICs, and the next model that we have is with population, income, murder, HS grad plus frost, which means we have removed area and we have removed illiteracy from our model. So, we go on performing the same steps over and over again. By performing the same test over and over again, we mean that R performs the test and finally arrives at a model where we have only those variables, predictor variables in the model which are significant, and all the others are removed. So, the final model that we have here after using the step function in R is the one that contains population, frost, HS graduate and murder as the predictor variables. The second method of selecting variables in a regression model is the forward selection method. This method basically performs the reverse of the backward elimination method. In backward elimination method, we had started with the entire model which contained all of the predictor variables and then eliminated one predictor variable at a time. In case of forward selection model, we start with no variables and just the intercept term, and then we add one variable at a time at each step and check the p-values corresponding to each of these variables. Now, if the p-value is greater than alpha, we retain the variable, else we reject it and move on to the next step and repeat step 2. So, here is the use of step function again in R with now direction as forward. So, when I perform the step function in R on the LM object using the direction equals forward, the first model is the one where life expectancy is regressed only on the intercept. Now, unlike in the backward elimination method, here you will see the table where each of the predictor variables are listed with a positive sign next to them. So, this means in each of these cases, we add one of these predictors at a time and obtain the AICs for the models. So, like here we have added murder, which means life expectancy regressed only on murder, and we obtain the corresponding AIC as negative 14.609. Then we had removed murder and included illiteracy. So, now we had life expectancy which was regressed on illiteracy, and we obtained the corresponding AICs, and the same was done for all the predictor variables present. And then after ordering the AICs, we see that the one model with murder as the predictor variable had the lowest AIC. So, we remove murder from the list of predictors. So, we now include murder in the list of predictors and move on to the next step where we include murder and add the other predictors one at a time and obtain the AICs. Again, the AICs are ordered, and the one with the most significant AIC is now retained in the model, which is for HS graduate, and we perform the same steps over and over again until we arrive at a model which contains all the significant variables and does not contain any of the insignificant ones. And if you look at the significant model here, they contain the same predictor variables that we had selected in case of backward elimination method, which are murder, HS graduate, frost and population. The third method of selecting variables for a model is the stepwise regression model. This method is a combination of both forward selection and backward elimination of the predictor variables. We start with no predictors, just like we did in case of forward selection, and at each step we enter or remove predictors based on the partial f-tests. We stop when no more predictors are statistically significant in the model. So the steps involved in performing a stepwise regression are: we first fit each one predictor model and in each case compare the p-values for the predictor to decide on which one stays and which predictor does not. Suppose out of the pre-predictors x1, x2, xp, x1 is the best one, that is the one predictor model with x1 has the lowest p-value. We now fit the two predictor models with x1 included in the model and regress y on x1, x2, x1, x3 and so on. Now suppose that the model where y is regressed on x1, x2 is the best two predictor model. We now step back and check the p-value for beta 1. This p-value tells us whether x1 is still significant predictor after the inclusion of x2 in the model. If the p-value tells us that it is significant, we retain it in the model. If not, we remove x1 and the model is now left with only one predictor, which is x2. Suppose both x1 and x2 are significant, then we fit all the three predictor models that include x1 and x2, like y regressed on x1, x2, x3 or y regressed on x1, x2, x4 and so on. And we continue with the steps until we come up with a model where adding an additional predictor does not yield a p-value below the critical value. So here is the R code for using the step function to obtain the parameters which are significant. Here is the use of R to use the step function to find the predictors which are significant using the stepwise selection method. So in this case we use direction equals both, and as we can see it starts with the entire model, and just like backward elimination we can see in the following table that they have actually started removing one predictor at a time and then obtaining the AICs, and based on the ordered AICs we remove or add the variables in the model and obtain the AICs for the next set of predictors. And these steps are performed every time we see that one or more of the variables are insignificant and they are removed from the model, or when we obtain one or more variables which are significant and we include them in the model. Finally, we arrive at a model where adding the predictors which are significant is complete for the model and no other variables that we have are significant enough to be added into the model. Here again we can see that the four variables that we have added are population, murder, HS graduate and frost. But there are several drawbacks of stepwise regression. The final model after using a stepwise regression is not guaranteed to be optimal in any way, which means after using stepwise regression, when we arrive at a final model which contains only the significant variables, we cannot say or we cannot guarantee that this is the optimal set of variables that should be added in this regression model. Although the procedure yields a single final model, in practice there are often several equally good models. The researchers' knowledge about the predictors also help in defining any other alternative to the model that we had obtained using stepwise regression and is not considered under stepwise regression. The use of R functions to perform model selection. Here we will talk about two other functions in R that we can use to select significant variables for a regression model. We can perform a version of backward stepwise regression using R function, add term and drop term, which are in the package mass. These functions will allow us to use the F-test criteria or a p-value criteria. Before we begin to decide on a level of significance alpha against which we compare our p-values, for the examples that we will illustrate in the next few slides, we have alpha equals 0.05. Now, we have used library mass in order to use these functions add term and drop term. So, we had used REG function, we had named REG as the LM object of fitting life expectancy on all the variables that were available to us. So, we use the function drop term on the LM object regression, and the test equals F will give us the F-test statistic, which will help us retain the significant variables and delete the ones which are insignificant. So, here is the output. We have the output, we have the S sum of squares corresponding to each of the predictors that we have. We have the AICs and the F values, and based on the F values, we can decide on which predictors are significant and which predictors are not. And we also have the corresponding p values for each of these F values, which will make the comparison of the p values along with our alpha easy to retain the ones that are significant. In the above example, we assume that alpha equals 0.05, then we have compared the p values of all the predictors and dropped the insignificant ones. Now, after dropping the predictor, we now fit the model again, and using the drop term, we repeat the process of removing the ones that are insignificant and retaining the ones that are significant based on the p values that are below the chosen alpha. And here is the output from adding the function add term in R, and we can interpret the results of using this function the same way as we did for the function drop term. So, as we have seen in this module, variable selection is a very important aspect of fitting a regression model, especially a multiple regression model where there are a number of predictor variables or independent variables involved. Sometimes when we have a large number of independent variables, we need to remove the redundant ones and keep the ones that are significant. In this module, we have learned three methods: the forward selection, the backward elimination, and the stepwise inclusion of variables in a regression model.